Once it starts, sorry for that, but that's pretty usual. And still, we have a round of 3 teams here or 5 to 3 teams here, so we are not that much under pressure. I guess most of you know me already. My name is Martin Plesch. I'm the president of the tournament. Otherwise, I work in the field of quantum computation and quantum security. And recently, I also decided to go for teaching future physics teachers, so that we have future physics students at some moment as well. And I'll be your chair today. So I'll now invite the teams to introduce themselves. Then the jury will be introduced, and then we go for the fight. A few remarks. Yeah, notoriously known. No internet connection. No attempts to communicate with anyone else in the room. Recordings are possible. Please no live streaming. And yeah, what is live streaming? I think we don't want to discuss whether 10 minutes are enough or half an hour. Like, not during the fight, okay? So like while the fight is running, nothing, like the recording should not leave the fight room. Once the fight is over, do whatever you want with it. Due to fairness, we will be strict with times. What does that mean? When the preparation phase is over, you will announce it and just immediately start the speaking phase, or how to call it. When you spend extra 12 seconds for preparation connected whatsoever, that's your time. When the speaker's phase finishes, you also announce it. Please finish a reasonably long sentence. So let's say one breath, okay? And that's it. The best fight is if the first time I have to stand up is to introduce the jury questions, and basically you manage it by your own. For the juries, we also have only 5 minutes. We are, as you see, there is a big crew of jurors. 3 of them will be non-voting, so you won't see any grades from these 3 jurors today. Hopefully during the next days. So posting questions is primarily for the 5 of us. If there is time left, I'll give you a chance. We just agreed among us as chairs that still you are more than welcome to prepare a question in written, so that we can somehow also check your, say, ability to guess what is an appropriate question. You're not asked to, but like if you feel you would like to post a question, then just write down the question into the score sheet. You can just very briefly write it, and then we can discuss. We will discuss during the break about like your grading and filling the score sheet, etc. One advice for you to keep the time reasonable, and that's for everyone. Please try to fill in the score sheet during the breaks already, because then like first one forgets quickly, and second it's also like a lot of time to fill in the score sheet afterwards. You can always correct yourself. There are always correction positions on the like minus points for the questions, etc. So now I would like to ask the teams to introduce themselves, please.
Okay. Well, welcome everybody. We are a team from Poland, and our team members are Krzysztof Maksymowicz, Piotr Baczereli-Biobelny, Mateusz Tarczyński, and Błażej Gorzałek. My name is Zofia Makowska, and I'm the team captain. And I would like to wish everybody a pleasant fight, I guess.
Thank you.
Hi everyone, I'm the team captain from Team Taiwan, and here are my members. So this is Oscar, this is Kai Cai, this is Andrew, this is Justin, and you can call me John. And then we hope you have a great fight also. Thank you.
Thank you. From Nepal, please.
Hello everyone, I am Saurabh Shrestha, team captain of Nepal, and we have members Pragyan, Pratyush, Ayush, and Sita. Hello. I hope everyone enjoys the day.
Thank you. And we can continue with Emily.
Good afternoon everyone, my name is Emily Kurtik. I'm a former participant, participated in 2016 and came back several times as team leader and now juror. I'm a PhD student at the University of Cambridge working on early universe cosmology. Wishing everyone a good fight.
Okay, let's have a big applause then for everyone, okay?
Hi, my name is Jayhun. I'm a team leader for Team Uzbekistan, who is participating for the first time. Previously, I brought Team Azerbaijan for the first time and Team Turkey for the first time. So next year that will be Morocco. Yeah. So I've been with IYPT since 2014. Wish you all good luck.
Okay, thank you. Apostolos?
Hi, my name is Apostolos. I am from Greece and I wish you good luck, everyone.
And you are very happy because Apostolos always serves only during the first round, so it's not an
Okay,
easy to
so
get
this
him
is
as
a
a juror.
privilege that you can have me as a juror because it's just one spare tournament.
Patrick?
I am Patrick Fans from Hungary. I'm former participant in 2018 and 19, and then had the Hungarian team prepare, was a juror in Pakistan and team leaders, organized the tournament last year, and I'm a theoretical physics PhD student at the University of Oxford. And I wish everyone a pleasant flight.
Okay, thank you. Ayan?
Hello everyone, I'm Ayan Pal, PhD student in Lund University, and I'm currently working with pure science matter physics. And it's my first time in IYPT, and I wish every participant all the best.
Okay, thank you very much.
Hello everyone, I'm Senja. I am the team leader of Team Switzerland. I participated myself in 2013. It's the first time I'm a juror here.
Hello, I'm Gianmarco Sasso. Last year I came as team leader for Italy. Now I came as juror, and wish you all a great physics night.
Okay, thank you. Now it's done. So now we can proceed to the challenging procedure. As this is the first round, basically there are no limits except of not rejection more than 8 problems, which I don't really from the team of Poland. So please change the page. No, so you are the reviewer. You are okay. So please step up.
Timing 9 minutes.
Okay? We accept the challenge.
Okay, thank you very much. Do you bring the two immediately or you need 1 year for Selena? So that's great if you can have that like a bit later. We have a visa policy of Sweden now is ambiguous. Yeah, but actually usually of course once you
Yeah, that's something interesting. Also that you can solve exactly like special equation. You can solve exactly like calculating stuff on that. Actual state in this will be out next week. But like on archive. Yeah, it should be working back on solving.
And the code is 1, 3,
of the magnet to the vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. On the video, we can see that when the rod is spun, the magnetic rod also rotates and climbs up, as said in the problem content. We are the area of the force application is a line. However, we are going to model it as a point by averaging out all the forces on this line. And when these forces will be more on one of the sides, we would get a displaced point force. When we have a rod attached like this to the ferromagnetic rod, we have a force of gravity which acts on it, and the magnetic force which attracts it to the ferromagnetic rod. The reaction force, and the force of friction which counteracts the force of gravity. They all result in the torque which wants to rotate this rod, so the load point displaces vertically so that the torques balance out. Similarly, in horizontal direction, when the rod is spun around, it generates a friction force which tries to rotate the rod and which creates displacement of the point of the force application. When we have a displaced load point like this, the friction force is not applied at the center, which creates torque, which spins around the magnetic rod. And when it's spinning around, its relative velocity at this point of force application is pointing slightly downwards, which result in a friction force upwards, since the friction always works in the opposite direction as the velocity. As we discussed, we have two important parameters describing this phenomenon: the displacement in the vertical and in the horizontal direction. We are going to model this magnetic force by summing the forces from all of the magnets and averaging out the load points. And since the far magnets generate a lot less magnetic force than the close one, we assume that the force doesn't depend on the number of the magnets. In order to calculate the displacement of the vertical load point, the load point in the vertical direction, we're going to use the torque equilibrium, since the load point will displace so that the torques are in equilibrium. Similarly, in horizontal direction, we write down the equation for force and the torque, and calculate the displacement at which the torques are in the equilibrium. In order to calculate the movement of the magnet, we can calculate the friction force, which depends on the reaction force, which is just the force of magnetic attraction, and we can write the components of the friction forces, which are the same as the components of the velocity, since the friction always works in the opposite direction as the velocity. We can get the velocities in both axes by adding the velocity vector from the rotation and the upward movement of the magnet, and we assume that the magnet will accelerate to such a speed that they don't accelerate anymore. So we can write those equations for the balance of the magnetic force with friction and the balance of friction torques on the magnets, and we can calculate the velocity from this. In order to model the force of the magnetic attraction, we use a dipole model. We approximate our magnet as a dipole and calculate its magnetic field. And we have measured its dipole moment using a Gaussometer at some distance from the magnet, which we measured using a millimeter paper. And we have fitted the magnetic dipole moments. And as you can see, this model doesn't work for small distances. And since we are working with very small distances in this problem, we are going to need another moment for the model for the magnetic field. So we are going to assume that the rod of neodymium magnet is a uniformly magnetized cylinder, and we are going to integrate it to calculate its magnetic field. And as you can see, when we fit the magnetization to the measured values of the magnetic field, it correctly assumes the magnetic field from the magnetic rod. And we have also measured this for
multiple magnets of the rod, checking if adding the magnetic fields from all the magnets results in the correct magnetic field value, and it does, as you can see on this graph. In order to model the attraction of to the rod, we assume that the dipole moment in the rod is linearly dependent on the magnetic field which it is located in, and this is the correct assumption since the magnetic fields are not high enough to get the saturation effect on the ferromagnetic. And using the formulas for the force of attraction between dipoles and the magnetic field, which we derived after, we can calculate the magnetic force. But we need to fit the parameter describing how the rod magnetizes. So we use this setup with a magnet attracting to a rod, which is put on a scale. We measure the distance between them with a caliper, and we measure the magnetic force with a scale. And using our measurements, we have fitted the parameter describing the magnetization of the ferromagnetic rod. And we have checked if this way of calculating the force is good for when we have more magnets. On this setup, in which we attached a bucket to the magnets and we poured the water until they broke off, and we measured this with a scale. And we have took the final measurement of the scale as the force of the magnetic attraction. And as you can see, our model correctly describes the magnetic force of attraction of a rod to the ferromagnetic rod when we have more magnets in it, and it also, our assumption from earlier, that the force doesn't depend on the number of magnets, which is the length of this magnetic rod, is correct, since when we have long rods, the force doesn't change anymore. We have measured also if our model correctly describes the forces in other axes when we have displaced magnets. And as you can see, it correctly describes how the force in the axis pointing towards the ferromagnetic rod decreases when we are displacing. And on this setup, we have measured the force in the horizontal direction. And as you can see, our model, when we displace the rod from the magnetic rod, and we have measured the force with a scale. And as you can see, our model correctly describes how the force in the axis perpendicular to the magnetic rod grows with the displacement. In our equation, we also had the friction coefficient, since the friction is the force which drives the magnets upward. So we needed to measure that, and we used this setup right here, where we put a wooden element on one of the magnet, which we knew the force of attraction of, and we were sliding it down on the ferromagnetic rod, and we have tracked its movement to get the acceleration, and from this acceleration we could calculate the friction coefficient. And using these equations which we derived earlier, we could then calculate the velocity. On our setup consisted of a motor, which and the speed of this motor we were controlling using a power supply. We attached a ferromagnetic rod to this motor, and the rod which was limiting the motion of the magnets to the vertical axis. And we have measured the rotational velocity of the rod using a tachometer, as you can see on this video. I have considered two methods of blocking the motion of magnets: attracting to another ferromagnetic rod at some distance, and blocking by a non-ferromagnetic rod, which was put near the end of the magnetic rod. And as you can see, both methods are viable to block the movement of magnets in the horizontal direction. And since both methods are effectively applying the force to the magnetic rod near its end, they should work
similarly, and the friction on the blocking rod and the decrease of the attraction force by a second magnetic rod are neglectable, as you can see from these numbers we have calculated from our theory. And as you can see, our measurements for both blocking methods are similar, meaning that both blocking methods are viable as to block the magnet's motion in horizontal direction, and they don't interfere with the experiment greatly. Parameters which we will investigate were the rod's angular velocity, the number of magnets, magnetic rod mass, and the magnetic force. We changed the magnetic force of attraction by using different magnets. We changed the number of magnets by adding more to the rod, and we changed the mass of the magnetic rod by adding plastic into it. As you can see, our theory correctly describes how the spinning velocity grows with the rotational velocity of the ferromagnetic rod, and as you can see, it's linearly dependent. Similarly, it also correctly describes how it changes with different magnetic forces, with weaker magnets attracting climbing slower. We have also measured how the climbing velocity depends on the mass, and as you can see, magnets with lower mass climb faster, and we have also measured how it depends on the number of magnets with a rod, and as you can see, it then when we add more magnets, it starts to climb faster. Since our magnet is longer and the load point displaces more. However, when we add more, the mass grows and it climbs slower. So in summary,
I'm sorry. Thank you very much. Questions from the opponent?
So could you turn to slide number 4? So you talk about averaging out the forces over the contact line. Could you describe the process of how exactly you're doing that?
We are not doing this in our calculation. It's just a way of describing how we model the contact force as one point force.
Could you turn to slide number 11? So is there a discrete model of how you describe how the contact line shifts? Is D expressed in terms of something else, preferably angular velocity?
We have calculated how the load points shift depending on the.
So is it a continuously occurring process that we consider differential displacements of D, or is it a fast occurring discrete process? Because we hear collisions, right?
It's a fast process, and the collisions are just the magnets rotating.
Could you turn to slide number 12? Okay, could you turn to slide number 15? I'm sorry. So here you've assumed that the magnets don't really accelerate much in order to write the equilibrium equations, right? So what's the basis of that assumption?
We assume that they accelerate for a very short time, and when they accelerate, they reach a certain velocity for which the forces will be balanced, so they cannot accelerate more.
Thank you.
Which one?
16, please. The one after this. You use the surface currents model in order to model the interaction force. So how exactly do you go on to calculate the surface currents along the surface of the ferromagnetic rod?
We are not calculating the surface current. We just on this slide we can see. I tell you that I used the dipole model, and then I showed that the dipole model doesn't really work since we are close. So we integrated the uniformly magnetized cylinder to get the.
Okay, thank you very much. Time preparation.
Can you turn the screen a little bit because it's invisible from there? Thank you. Okay, I forgot.
your time is running.
So the opponent had both strengths and weaknesses. His major strengths were with exploration of both ways in order to model the interaction force between the long magnetic chain and the ferromagnetic rod, namely the Gilbert model and the impedance model. Next is accurate vectorial expressions.
Can you at least make it full screen? So because like this is completely unreadable for us. Like F5.
So reviews accurate vectorial expressions and usage of equations of motion, torque equations in Newton's second law, in order to fairly precisely make theoretical predictions regarding the time rate. And next is they had good experimental control. I'm sorry, we're having a bit of technical issue, but they had good experimental control regarding their measure of angular velocity and the magnetization of the rod, and the magnetization and magnetic field along the perpendicular distance on the axis of the rod. The weaknesses are they don't describe the effect of hysteresis since it is a ferromagnetic rod. Next is they had a bit of an ambiguity in usage of symbols in their expressions. And next is they did not describe whether or not the climbing rate depends on the vertical position since it isn't an infinite rod. And so their assumptions regarding the equilibrium conditions, which they used in their force expressions, were insufficient. Thank you so much. So my suggestions to the reporting team are that they consider hysteresis since it is a ferromagnetic rod, and over time as you change the magnetic fields around it, effects of hysteresis might come into play or might not come into play depending on how they reason it. Next is they label their parameters in their force expressions so that we have more clarity in understanding it. And describe also accurately whether or not the climbing rate does indeed depend upon the position, and also fairly reasons regarding why they assume the equilibrium conditions.
Right, so please proceed to the discussion.
So, did you make any effort whatsoever in order to model the electrodynamic forces in other regions apart from the perpendicular distance, wherein the magnetic chain has?
So we modeled the magnetic force, just assuming that the rod is magnetizes linearly, depending.
So what is the basis of assumption that the rod doesn't magnetize?
So the rod magnetizes linearly because the magnetic fields around it are around a half of a Tesla, and the saturation magnetization and the hysteresis effects come into play only around 2 or 3 Tesla. So we can use this linear model to.
What are the boundary conditions? So can you tell me about the boundary conditions that might be imposed on the rod surface on a circular perimeter of the rod, if I were to consider one element?
We are. I don't think we understand each other about how we calculate the magnetic force. So in my model, we just calculated the magnetic field in the point where the ferromagnetic rod is, and we assumed that it has a magnetization which is linearly dependent on the magnetic field which is given, and we just use the formula for the attraction between the poles. And we sum the forces acting on all of the magnets to get the force.
Thank you so much for the clarification. Could you turn to slide number 32, please? could you clarify exactly how we obtain this expression regarding the force?
Okay, so this is the
And
just,
regarding the symbols.
so this is the integral. So we integrate the magnetization by the volume of the rod to get the magnetic field. For example, R is the horizontal displacement.
Okay, so do you agree that it would have been more gratifying if you attached a diagram with all the parameters labeled?
Might be a little bit more clarifying if the parameters were labeled.
Okay, could you describe how exactly you proceed to this long force expression with all these dot products regarding the interaction force?
So this is the interaction force between the magnetic dipoles. So this is just the typical formula we use to describe the force between two dipoles that are pointed at some angle away from
this is the derivation.
So this is just the typical formula we can find in many publications of physics.
Could you please tell me what alpha is?
Alpha is the parameter that describes the magnetization of the rod. We assume that the rod magnetizes linearly depending on the magnetic field which it is located in. So B is the magnetic field and alpha is the magnetization of this.
Could you turn to slide number 22, please? You mentioned how more magnets meant better force modeling. Is that correct?
I didn't mention that it's a better force modeling. I thought that we assume that when we add more magnets, the magnetic force doesn't grow, since when we have many magnets in the rod, when we add more magnets, they are far away from the ferromagnetic rod, and the attraction between a magnet and the ferromagnetic drops around 1/r to the 7th power. So when we add magnets far away in the rod, it doesn't increase the magnetic force.
Thank you for the clarification. Why is it that the dependence is 1/r to the 7th?
Because the magnetic field is 1/r to the 4th, and the magnetic field is 1/r to the 3rd, and the force of attraction between dipoles is 1/r to the 4th. So it's
Attention at the exponents. Thank you. So in a typical way of how we spin the axis around, it's generally that the magnetic rod axis precesses around the central axis. In other general exemplifications of this same experiment. So have you considered that case?
Well, when I performed the experiment, I didn't observe it precessing. I observed that the magnetic rod was rotating around its axis, and its axis was just slightly displaced from the axis of the ferromagnetic rod. So it was just not pointing straight to the center of the ferromagnetic rod. This is due to the friction between their surfaces, which pushes the magnetic rod. However, they are both spinning around their axis.
So what I was saying was the rod in and of itself precesses around the surface of the cone. When we generally can exemplify this experiment in homes, right? You use a model wherein the rod's axis was fixed and the rod was spun around the axis, right?
Yes. And when I was performing this experiment, I didn't observe processing around a cone. I observed that
these are conditions that you set by yourself.
No, I thought that the load point displaces. However, as you can see on this video, the magnetic rod just climbs upward and spins around its axis. And what I said was that the load point, so the point where the magnetic force is applied, not the magnetic, but the reaction force is applied, is displaced slightly into the downward part of the magnetic rod to balance out the torque of the gravity. We have that on. Right here you can see that we have the torque of gravity, which tries to hold down this magnetic rod. So this displaces the point, the load point, but the magnets are not displaced since they are in contact with with the entire surface.
So you did not consider the case wherein the magnet in and of itself rotates around the magnetic chain in and of itself rotates around the center axis.
No, we didn't consider this since the problem content tells us to block the horizontal motion.
What point exactly have you written the torque expression against?
The torque expression was written around this point of contact.
You talked about the axis of contact being displaced, but you're saying that the torque expression has been written about it.
Yes,
A point.
it's written about this point in the center of the magnet. So
In the center of the magnet?
yes, in the center of the magnet on the contact on the contact surface.
Which has been shifted or which is
No, the magnets are in contact with the entire surface as I have shown here. They are in contact with the entire with the surface on the entire line. However, since the modeling of the forces on this line would be hard, we just average them out and assume that they act with a single point force.
Thank you so much.
Thank you.
So, okay. Is that all? Okay, thank you very much. Do you want still to have this 1 minute summary of your opposition? Okay, okay. So then we can skip directly to the questions of the reviewer, please.
So first of all, I think the key point here should be driving up. So I think what is the mechanism of transfer force upward?
So the magnetic rod starts to rotate because the torque of the friction force acts on it, and when it rotates and the contact line is slightly displaced from its center, the relative velocity is downward. So the
pushing the velocity downward at the contacting line.
Yes, on the contacting line the velocity.
What is the mechanism of transferring force upward?
Yes, sir. Could you please repeat the question?
What is the mechanism of transferring the force upward?
What is the mechanism of?
Transferring a force upward.
Causing the force upward. Why the force upward?
Okay, it is because the frictional force acts opposite to the direction of relative velocity.
Okay, good. So do you observe any horizontal direction of displacement will change?
No, I have observed that well, it doesn't change when I increase the rotational
So you
velocity.
observe it when you increase the rotation?
No, I
You
did not.
didn't observe the changing of the horizontal displacement?
Could you?
Did you observe the horizontal displacement change with time?
I didn't observe it change when I increased the rotational velocity.
Okay, so what is the meaning of a plot? Because you said, because I see that there's a plot is you fit the plot and unplot condition, but they fit to the same theory. So what is the meaning of the plot? So plot limits the.
Oh, the blocking rod.
Yeah.
The blocking rod is necessary, so the magnetic rod doesn't just attract and spin around the ferromagnetic rod, since this would occur when we have no blocking rod, and we need to block it, so it can just slightly displace, not spin around.
For a minute, I think you mentioned that the port is not equivalent for the motion, right? So yeah, because I think the main reason is because the reporter made an assumption, which is acceleration equal to 0. Do you think that assumption is reasonable?
No.
You don't think?
It might be reasonable, but you will have to clarify that further.
Okay, well, so did you measure acceleration? So you check the acceleration equal to 0.
The acceleration period is very small, so
Did you measure gravity?
So I did not measure the acceleration, just the velocity.
So what is the main parameters affect the climbing rate?
The climbing rate is affected by many parameters, such as the rotational
This
velocity.
is only one main parameter, most important.
There are many important parameters.
Okay, so next time. So what is the effect? What is the difference between the width and the number of magnets?
So when I increase the number of magnets, the rod is longer, so the gravitational torque is higher, so the load point.
Also, it's about the gravity torque. Right?
Yes, it's about the gravity torque. So the load. so the load point decreases, the torque from gravity increases more.
Okay. Sorry. Thank you very much. Please, I'm sorry, I don't see the screen, so please also shout at me. Because no chance for me. Okay, time for preparation of the question.
Hello, I'm Zheng from Taiwan. I want to review number 40 and 4 cutting magnet. As a proper statement, I think a key question should be the force causing a magnet turning upward, and also the effect of each parameters and the mode of driving. I think this needs to be mentioned. And for review for report, it has a simple phenomenon demonstration, and I think that, but I think that should care about the motion of the magnet, and also it did not compare different directions of motion together to let us know about how the magnet moves. And also for a theory and model, they model the force on the line, and they think that line should be a conducting line. And also they find that there's a horizontal displacement between the center of the magnet and the conducting line. And there should be a torque, and they think that it uses a torque balance, and which means that torque from friction will causing a horizontal displacement. And they also assume that rod has a uniformly magnetized cylinder, and they think that it is a linear region induced by the magnetic dipole. So I think that they do a great job on characterizing the magnetic extension, but I think that too much emphasis on the magnet should have more emphasis on friction and driving upward. And for the experiment, he did a wide experiment range and had a good agreement, but I think that means a lot of parameters like the critical condition of no climbing, which is a boundary condition. And also, I think he should have investigate the horizontal displacement because he didn't mention and he didn't show a video about it. And for data analysis, I think that's true. And for review of positions, for presentation that he mentioned something about the reporter, but I think that he missed about the horizontal displacement and the interpretation for parameters, because they say nothing about parameters in the presentation. And for short questions today, clarifies well, but they did not connect it to later discussions. And for discussion part, first discussion about the reasonability of a linear magnetic rod, and also the boundary condition on the rod surface. And then talking about the derivation for magnetic force and the effect of the number of magnets and connecting with rod. And for this point, I think that we do not consider about critical condition for climbing and no climbing, because that is a really important boundary condition about this. And also, I think that he taught a little bit, but not much about unstable climbing. And he did not. I think the discussion did not add to understanding of presentation and phenomenon. And for key discussion here, the first one I asked is reasonable to assume that linear magnetic extension of the rod, and reporting it is because the magnetic field is pretty low. But I think there's no reason to assume that linear relation. There's someone nowhere. And for our questions, we think that I'm asking what is the mechanism of causing a force upward, and the report say that it is because of the rotation and horizontal displacement causing a conducting line has a downward velocity, and it is said to me. I think it is also caused by this. And I asked for both of it, that is the torque and the equivalent is reasonable or not. And I think that the reporter said that because the acceleration is very small and it is not measured, so you think that it is reasonable to think that the acceleration is equal to 0. And the reporter think that they should verify it, and I also think that the reporter should measure about it, because we can't just say it looks like very small, and so just do this assumption. So that is quite important. And for the horizontal displacement, I asked the reporter, do you observe the horizontal displacement in the time? And the reporter answered, no, observe. And also I asked about the meaning of blocking rod. So the reporter answered is to prevent the magnet from spinning around the rod. But I think, except for this reason, it also has a reason to has the causing the friction has a torque, causing a horizontal displacement will change the time. I think it's and also causing a horizontal displacement has a bigger displacement while you increase the distance between the bottom of the magnet and the blocking rod. And I think that is my presentation. Thank you.
Okay, so the reviewer told that I didn't measure the acceleration since I said it was very small, and I would like to clarify that. I didn't mean that the acceleration in this setup is very small. I actually meant that it lasts for a very short period of time, since it's actually quite high acceleration, and it causes the magnet to quickly reach the velocity at which all of the forces are balanced. And when they reach this velocity, they are just climbing with this constant velocity. That's why I did not measure the acceleration of the magnets. The reviewer also asked about the most relevant parameter that affects the motion of the magnets. So, well, the rotational velocity of the rod is an important parameter that influences the motion. There are also many other parameters that I investigated, such as the number of magnets in the rod, as increasing the length of the rod can result in the load point displacing more, which generates more, which creates more velocity, which results in a higher climbing velocity. However, it also increases the mass, which also increases the mass of the magnets, meaning that it's there is more friction force required to balance it out, resulting in lower velocities. So I think that there is no just one relevant parameter that describes the motion of the magnets, and but there are more parameters which we investigated, and as you can see, our model accurately describes the climbing velocity, since we wrote down all of the mechanical equations and all of the magnetic force equations. Thank you.
Please stay connected. Sure. Questions from the jury members, please. Okay, I have a quick one. So, show me one of the linear theory graphs, say the climbing velocity from the rotational velocity.
And this one?
You had the climbing velocity from the rotational velocity. Did you have that?
Yes, this is the.
This is angular velocity. This one. So you say it's linear.
Yes.
So do you have a formula? Can I see a formula?
Well, I have a formula right there. As you can see.
So where is the climbing velocity here?
Well, there is not
a
final formula. This is just a system of equations.
Can we see the final formula?
Well,
which
there's not one final formula, but it's just a large system of equations. There are more equations to it for the displacement and for the magnetic force.
You are displaying on the graph for linear dependence, so the formula has to have a form something like velocity is something times omega.
Yes.
So I would like to see this kind of formula if there is a linear dependence.
This formula is quite large and complicated, since it consists of many equations. These are one of these equations, but we also have these large equations for the magnetic force and the magnetic field and for the displacement. So this formula is quite large, and we did not put that on the slide.
You have it somewhere.
Well, I can't write it down from the memory, but I would derive it from these formulas, but it would take a few minutes, since I have these long equations.
Okay. Patrick?
Continuing Martin's question, does it come out to be linear, or omega is hidden somewhere in the different equations, and in that section it turns out linear, and
No,
the other
it
values
turns
will
out
be something.
linear
Okay.
for all of that.
Thanks.
Further questions? Jehon?
I would like to ask, can you go to the slide where you show the relationship between the number of magnets and velocity?
No, it's this one. The velocity.
So your minimum number of magnets, what was it, 15?
It was the minimal amount of magnets, the number of magnets that I took experiments for.
So you did an experiment with less than 15 magnets?
Yes.
Okay. Apostle?
Okay, one question about your graphs. The lines you have here is according to the theory, or you just draw a line through your
No, this is the theoretical line from this equation of this equation of the mechanics and the magnetic.
Sorry, yeah, please.
So this is the theory line,
Yes.
and you have your experimental the blue bullets. And how do you explain that sometimes you have higher experimental values than your theory predicts?
Well, my theory.
And how do you
also has
calculate
some,
this wide of errors?
Well, my theory, they are not that far from this theory, and my theory also has some experimental errors.
That's my question. That was my question. How broad is the theory? So, like, what is the error of the theory? You have one line, but how broad the line should be?
The line should not be that broad, but it should be around similar to these error bars that we can
Patrick?
see.
I want to ask you a question that relates to the reviewer's question. Did you see anywhere where you put some magnets there and it doesn't move upwards? So did you see some critical effects?
Well, there are
even
critical
downwards,
effects
or
when
even downwards.
When I have too low friction, for example, sometimes when all of the friction points upward, it doesn't create enough force to counteract the force of gravity, and the magnet just slides down.
Okay, so sometimes you saw these
Yes.
effects. Okay.
Okay, so then, like, if you say the theory is always linear,
It's the
So, because
theory. So the theory is for the relation between the climbing velocity and the rotational velocity.
so can you show the
of
graph again?
Right. So it is for the parameters that result in climbing, and when we have parameters that result in climbing, the velocity is linear. However,
Okay, but can I pose my question now? If it's linear, then it's 0, 0 always. No, like if it's truly linear, it's 0, 0. But at the same time, you say for small friction and 0 angular velocity, we would just see the magnet just sliding down. No, so but this is not what your theory would predict.
it is
Okay.
because this is for the one constant friction, which is
Okay.
high enough.
Okay, thank you very much. Time's up.
One thing is like we are scanning it. The one is like this will be probably hard. If you want that they have the access to it, then you have to write it a little bit. And also like this kind of like, especially if it's flag and it's just a point, the scanner will smooth it out as like as error. So maybe like a bigger. This depends on the scanners. Like now this will not be scanned. So it's just like for the future. If you, of course, whatever. It's just like if it's too tiny, then usually the scanner will like. We should
As usual, you can do whatever.
Not just me, not for the case, but in general.
Okay, for you, yes. In this very specific point, also the other candidate. No, it's just like even if it's 0.6 or something like that, no, it's just like there is some like also like this kind of like you shouldn't change 4 to 6 or vice versa.
Yeah, but not me.
Okay, you of course you can. Yeah. Why shouldn't but you can. So it's just 0. I will just remind the jury that we also have 5 minutes for grading. That includes showing the grades and explanation of yes. Okay, maybe we have to split it. I think we have to split it. Yeah, maybe it's good because if we just ask Felix to do it and just if it's a privacy decision, then maybe force is you can hardly force Felix to do anything.
It's like this force. Please do it.
Yeah, please do it. We rely so much on you. No one else can do it.
Presentation on the last fight. Not now.
Yeah, sure, please. No, the only question phase is this one. Okay, sure. Yeah. I think it's borderline, but I would allow it. But it's a kind of borderline because it's not their solution, but it's like the essence of the problem. So I would allow it if it's like the essence of the problem. If it would be like a technicality, then probably like the viewer is not the viewer is not one who should explain. The report is perfectly fine. Yeah, that's perfectly fine. So can you tell me why? Like in 2 sentences, why? That's fine. In this case, I would also allow it to the reviewer because it's the essence of the problem. But especially on the reviewer, didn't select like the opponent challenge and the report accepted. So it's possible that for the reviewer is a pretty, like unknown field, let's put it this way. So it's not very fair to push them into asking questions because they might not. No, but like I agree, as he already went it, I would say it's fine. Okay, guys, come on. Like if it takes now 6 minutes, what will you do in the 5th round when you will have compare it with everything else what was there before?
You want to check?
Yes, I have to check. It's like, come on, I already learned the reading it. I had the American guy at the finals and it's like, your sum is wrong. And he said, no, it's right. I said, it's wrong. He said, you can't see it. I said, I see it, it's wrong. I said, I used my calculator. I said, then your calculator is wrong. And then she's like, oh, it's really wrong.
I always have with my calculator, so I'm 100% sure.
I
Oh,
always
he used the calculator, he was wrong. So.
Because it's 1 to 10, I always count by hand. And if it's a half, I do this.
And then depends on how your finger is, then you go up and down.
Yes, it's
But never
two-thirds,
never
one
use
third.
just the middle one, okay?
Usually this is the one.
Jumps up now.
Better handling.
Okay, so yeah, time is one of the one of the things. So that's something. Yeah, I like it. It looks like a notebook.
They are expensive.
Okay, so I lost this.
Because I try to do it so I don't.
Okay, so give me the final numbers and let's go. Yeah, I want you to have the final number before we show ours.
My friend. Okay, well, what's the time?
Yeah, I know.
Sorry, I'm joking. I am not joking.
It's your first and last shooting experience. You need to enjoy it as long as you can.
Okay, so we are ready. Grades for the reporter. Now, can I start from the back? 6, 6, 6, 5, 5. Grades for the opponent. Now, 4, 3, 4, 4, 4. And grades for the reviewer. Now, 5, 6, 6, 7, 6. 5, 6, 6, 7, 6. Okay, thank you very much. I hope you have a paper as well. Can I borrow that one? Yeah, this one. I need to check who has the lowest and highest grade and ask them for explanation. That's the usual procedure. I'll give it back. Okay, so guys, it was very smooth. I have to say, without commenting directly, I have to say also the new jurors got very, very similar grading, which I'm happy about. So I like not much of commenting of the differences, but I think it would be good to comment on the points per set. So who would like to comment for the presentation? Yeah, please, Jason.
I think it's like they did a lot of things, but when it comes to the presentation, it's like I think both the like reviewer and opponent team, they were lost what's happening there. There were like lots of equations, but like the main point of the question, like you could have shown us, okay, this is the theory, this is the model, this is the equation, and this is the graph, and this is the parameter effects. But like all the questions, there are many, so the answer was like many parameters effect, but what are the crucial key points? Like, we know that there are many parameters, which ones are the key ones? And you could have concluded better the presentation.
Okay, Patrick, quickly.
Quick comment. I think the presentation focused too much on like measuring nearby things, like measure the magnetic force, measure this,
the
measure
magnetic
that.
force was too much
Like,
there.
not the most important type of measuring actually the phenomenon and seeing how the phenomenon works, but like you measured all of the little things around it, and you should have spent more time on like the actual.
Yeah, but also, my feedback is like you had a preliminary thing. Okay, let's write down the basic equation. That's fine. But then you have the final formula. You didn't say anything about like how to get from the equations. You had the final formula, and I'll be very open. I did this exercise by myself because I was really interested, especially as seeing like actually your solution in Greece, and I deeply disagree that it brings a linear solution. This is something I deeply disagree, and we'll discuss it probably on a different level, because this is like it's more complicated, and without like other assumptions, etc. Whatever. But like we didn't see. I was eager to see how you solve these formulas and how you get your results, and that's what I didn't see at all, and that's very important. And also, if you say the imprecision of the theory is as big as the imprecision of the experimental data, you should put it there, no? Because like you have one line, but like the theory encompasses many experimentally measured parameters with some errors. So like it must be seen there. Okay, the opponent, maybe Apostolos, you were the only one giving a slightly lower grade than the others for the opposition.
Opposition. Opposition. Sorry, I was confused. For the Nepal guys. Okay,
Nepal.
guys, I may seem now the bad guy. I think we all have 3 and 4.
Yeah,
okay.
that's not.
My partial grades are 1 plus 1 plus 1 plus 0.5, so 3.5. But I gave you a 3. I think you understand that this performance as an opponent needs needs improvement. I think you focus too much in one aspect of the report, but you didn't go further away. Also, I always, when I grade, I'm trying to be objective in my way by seeing this score sheet. So I couldn't go any higher from what it says here because I thought, first of all, in the questions, the clarified questions, I didn't see enough things. We can discuss later if you want. Then to your opposition, again, you focused on very strict things on the discussion because I had some questions for them about the graphs and the results. You asked none.
Yeah.
About the error analysis, about the results, nothing. So I think, okay, I know you're also new entry guys. I think second year, so maybe it needs to try to focus on everything. And also, sorry, one last thing about the, how do we say this? The English word.
You can say slower.
What is most important? I never say this word correctly. Prioritization. Okay.
Yeah,
about what you are asking.
Okay, just very like I see it over and over that like people are afraid of discussing the theory if it looks complicated. Come on, like if you didn't understand it, probably we didn't either. So if you go and discuss it, even if you like pose question, okay, so what is this F and what is this V and which one is this V and is this? It's really better than just discussing, you know, like some.
You can do like, can you explain me this part because this part I don't understand how you get. Can you explain it? And then the jury is happy that we also understand from that.
Yeah, because normally or very often it's like we couldn't also understand it.
And you have time for that.
Yeah.
And, okay. And also the other 4 guys that support the one here on the stage, guys, you see he's trying to ask questions. Try to provide him. Maybe if he's focused on one thing, try to provide him questions. Help him.
Okay. Very quickly for the review, maybe Emily, you had a 7, which was slightly higher than all the others.
Yeah, I thought it was a good review, well structured. I appreciated that you asked questions both to the reporter and opponent, and the questions were quite well prioritized. I like that you gave your own opinion and you brought up very important missed points that they didn't investigate the limits of the theory and the regime in which it won't fly. I thought that was an important point, but the thing that could have been maybe improved that you mentioned it was missed, but you didn't give your opinion on
your
the
opinion,
physics behind that, in your opinion. That could have been maybe summarized really quickly.
There was a question which was not posted by Jean-Marc about like, okay guys, you asked about why is it climbing, so why is it climbing? Like this is something you could say, you know, in like 20 seconds in your review that like, okay, this was not, like this crucial thing was not mentioned, something like that. Yeah, I also agree that I was missing like many interesting topics were touched, but I missed like your clear opinion like on this topic. So we said like, oh, this was the question, opponent thinks this, reporter thinks this, and because we are pushed by the officer.
I think like the discussion analysis was very short and you spent a lot of time focusing on answers to your question. Like as a reviewer, you should focus on their things, not like I asked this question and this or that. So it shouldn't be on you. You should be evaluating their discussions, not like their answers to your question.
Can I say something that maybe don't misunderstand me? I didn't agree with everything you said because what I saw, you have to be objective somehow. I didn't see everything I heard, I didn't see you write it in this way.
Okay guys, it was a very nice fight, I think very interesting presentation and etc. But we are really late. So let's have like a strict 10 minutes.